Okay, so if there is no doubt, then let us start to the lecture. So let me revise quickly what we discussed yesterday. So yesterday we discussed vector spaces. Basically, we are going to consider the vector spaces over the complete fields. So that means we'll be considering vector spaces in this course, which are real vector space or complex vector space. And we know all the axioms of vector space. There are 8 axioms. This first example anyway is not related to our course because, as I said, it is the field is different, right? And the second thing is this is a actually a field extension, which is a infinite field extension. So to prove that it has infinite dimensional, I think we need here abstract algebra. So if you remember in abstract algebra, there is a field extension. So if you see that the dimension of q root 2 over q is 2, and this is a extension related to the polynomial x square minus 2 is equals to 0, right? So here the dimension is 2, but there are so many such irrational numbers in R. So one by one we add, then we can observe that the dimension is infinite, right? So this problem is related to Galois theory, and we'll not go in much details because we only need some examples of vector spaces. So we discuss Euclidean spaces, that is Rn, Cn, matrices over complex number, matrices over real numbers. Then the function spaces, so functions defined on a fixed set which are complex valued or real valued, they form a vector space where the zero element is identically zero function. It has a subspace which is the set of continuous functions, right? So this fifth example is a actually subspace of the fourth example, where we are taking S is a this set, and we are imposing another condition that each function should be continuous. So zero element is here because zero function is also continuous, and then we discuss the set of all polynomials with pointwise addition and scalar multiplication is a vector space, and we discuss some idea that why it is a infinite dimensional. So this basis which we discuss in linear algebra, that basis is known as Hamel basis. So this two condition is there. The set is linearly independent and its span is whole space X, vector space X. That two condition is satisfied, then that set is known as basis in the vector space, and that was given by Hamel, so it is known as Hamel basis. So we know that there are different bases in linear algebra. One is a orthonormal basis, right? That is different from linear space basis. There we use inner product, and then we discuss some set theory. We define the notation conjugate of a function, finite set, denumerable set. Denumerable means countably infinite, and countable means either countably infinite or finite set. And then we discuss uncountable set. So the set which is not countable is uncountable. So then we define arbitrary union of sets, intersection of set, and then this last example. So did you try this example? So if we have a countable collection of countable sets, then its union is countable. So is it true?
Yes, sir, it will be true.
Yes. So what is the proof? What is the idea of the proof?
So the proof I am giving is actually from the BSc. Suppose this set I am arranging as A1, A2 up to AN plus 1 infinity.
Right.
So,
Let me write.
means we can, okay. So you are writing it, or should I
Yes.
say?
Yeah, yeah, you say I'm writing that.
Uh, Sir, if we can write their elements as A11, A12, if you can write them as like this.
Yeah, so it is in this kind of, yeah. So yeah, basically we can make a matrix kind of thing, right?
Yes, sir, yes, sir.
So this even is a countable sets. That means its element we can write as a A1, A2, A3, so on. B2 has B1, B2, B3, so on. B3 has, let us say, so instead of writing this way, let me write A11, then A21, A22, A23, and so on. And in third, E3 set has elements A31, A32, A33, and so on. And then what is the idea? Idea is we need to fill all these elements in a sequence form, right? So the idea is that we will fill all the elements diagonally, one by one. So that means we can make a sequence itself, the new sequence out of these sets, as the first element is A11, then the second element is A12, A21, right? So these and these, and then we will go A13, A22, A31. So that is third arrow, and so on. If we go in this way, then we can fill all the elements of E1, E2, E3, En and form a sequence. And since all the elements are contained in a sequence, that means this is there is a one-one correspondence with the natural numbers. That means it is a countable set. Yes, so you must have seen this proof in earlier in your BSc. Okay. So countable union of countable set is countable. Now we want to recall some basic definition related to equivalence relation and equivalence classes. So let us start with the definition. So have you studied equivalence relation in your bachelor's? So relation R on a set X is a subset R of X cross X. Right. So this is the definition of relation. So if we are given a set X, which is of course it is a non-empty set, and R is a non-empty subset of X cross X, then R is called a relation. And further we say that, so in definition of relation, the relation R is called reflexive if Xx belongs to R for each X belongs to X. So this is reflexive. The relation is transitive if whenever xy belongs to R and yz belongs to R implies xz belongs to R. Right, so this is transitive. The last condition is symmetric. So symmetric means so whenever xy belongs to R implies yx belongs to R. So whenever given relation is R is a relation on X which is transitive, reflexive and symmetric, then it is called an equivalence relation. So can you give some examples of equivalence relation? So a relation which is a symmetric, transitive and reflexive. So there are many examples. First of all, let me write down the definition of equivalence class. So the equivalence class of X is denoted by class of X, right? So that is the set of all elements in X which are related to Y. What is the example? Example is, there are several examples. First example is, we consider integers, set of integers is X. So if we divide the relation, so what is the relation? Relation is a subset of X cross X, and X is Z in this example. So that means we are taking two integers which satisfies certain property. So for example, we are considering the difference of these two integers that is divisible by 2. So that means let us write down it as 2 divides m minus n. Right. So which two integers will be in this set whose difference is divisible by 2? So can you give me some examples? What will be the elements of R? So basically what we
So,
need, yes,
so two classes will be one of even means both even term, and other will be odd terms.
odd terms, yeah. So first of all, this criteria is basically m minus n is equals to 2 times k for some k belongs to z. So that means all the numbers whose difference is even number, right? So basically 1 comma 3 is in R, 2 comma 4 is in R, right? Because the difference is even number, right? This is mn. So m minus n is minus 2, so that is a even number. So therefore these numbers belongs to R. Now the question is that whether this is a equivalence relation. So how to check? So first property is reflexive. So reflexive means for each m belongs to z, mm belongs to R. So is it true mm belongs to R? So that is true because the difference of m minus m is 0, which is 2 times 0, right? So therefore for every integer m belongs to R. Second thing is, if mn belongs to R and nl belongs to R, then what we get? We get m minus n is 2k for some k, n minus l is 2m. If we add these two, what we get is m minus l is equals to 2 times k plus, let us take some another number, p. Right, so m minus l is also even number, so that means ml belongs to R. So we check transitivity as a second property, and third property is symmetric. So that means if mn belongs to R, then what we get is m minus n is even number, right? And if m minus n is even, then obviously n minus m is also even, right? That is just negative of even number, that is also even number, and that will give us nm is also belongs to R. So this is the equivalence relation we already know, and once it is a equivalence relation, we use notation x is m is equivalent to n if m minus n is even, right? So now what you just now said, that if you find the equivalence class of 1, then by definition it is the numbers. So what is the definition? Definition is that y belongs to x is set of integers such that x and y are related. So here equivalence class of 1 is n belongs to z such that 1 minus n, so basically 1 is related to n. So that means what? That means n belongs to z such that 1 minus n is even. Right, so this will give us n belongs to z, and n we can write as 2k plus 1. So what are the n? N is basically of the form 2k plus 1, that means that is the odd numbers, odd integers. And similarly, you can verify that class of 2 will be all even integers. So that means there are only two equivalence classes, because class of 3 will be again odd integers, class of 5 will be odd integers, right? So up to there are only two different classes basically, is class of 1 and class of 2, it is odd and even integers. So the equivalence class is always forms a partition of the set itself, right? So here we can see that the x was what? X is a set of integers, all integers. And the equivalence classes we got is, there are two different equivalence classes. One is a odd integers and even integers. So we know that intersection of odd and even integers is null set, and its union is the whole set. So that means that is a partition of set of integers. Okay, so if we know this equivalence relation, then we can construct some examples of vector spaces. So new examples of vector spaces. So first example uses this equivalence class. That is, if we have a subspace of a given vector space, so let Y be a subspace of a vector space X, then using Y we can define equivalence classes. So how do we define equivalence classes in this case? So first of all, we need to define a relation. So define a relation R on X. So what is X? X is a given vector space. We are defining relation on that vector space using subspace Y by, so the definition is R is defined to be, of course, it is a subset of relation on X. That means it is a subset of X cross X, and we will define relation as x1 minus x2 is in Y. So x1 and x2 are related if x1 minus x2 is in subspace Y. Right? We are defining this relation. So clearly R is a subset of X cross X. So that means it is a relation. Now we need to check whether it is a reflexive, symmetric, and transitive. Right. So first condition is reflexive. So is it reflexive? So if you take any element of X, so whether XX belongs to R, for that what we need to check? We need to check X minus X should be belongs to Y, right? And we know that X is the element of vector space, so X minus X is a zero element, right? And Y is a subspace, so every subspace contains zero element, right? So XX is in R if and only if this condition is satisfied, and that condition is X minus X should be in Y. But we know that X minus X is a zero element and Y always contains zero element. That means this condition is satisfied, so therefore XX belongs to R. The first condition is satisfied. Let us check the transitivity. So for transitivity, we need to take three elements X, Y, Z belongs to X, such that X, Y, and YZ belongs to R. Right. So what does this means? This means by definition of relation, XY belongs to R means the difference is in Y. So that means X minus Y belongs to capital Y, and YZ belongs to R means again difference is Y minus Z belongs to R. Right. So sorry, that belongs to capital Y. So now to show transitive, what we need to show? We need to show YZ belongs to R. Right, and YZ belongs to R, that means we need to show Y minus Z belongs to Y by the definition of relation. Sorry, XZ. Right. So what is given? Given is this condition, and we want to show this. So can we show from this condition the other condition? Can we use some property of subspace?
Vector addition.
Right, so we can use the vector addition. So if we add this element in this element, right, because y is a subspace, it is closed under vector addition, so that we can use. So since x minus y belongs to y and y minus z belongs to y, and y is closed under addition, we get x minus y plus y minus z belongs to y. Right, so that means finally what we get, if we add these two elements, y will cancel out, so finally we get x minus z belongs to y, and that is nothing but xz belongs to r. So therefore we get the relation is transitive, and the final condition is symmetric. So symmetric, we are given xy in R, and we want to show yx is in R. If xy is in R, that means x minus y belongs to subspace. So now using this, can we show yx belongs to subspace? So here we'll use the second operation. So if y is a subspace, so that means it is closed under scalar multiplication. So if x minus y belongs to y, then minus 1 times x minus y is also belongs to y, right? Because closed under scalar multiplication. So y is closed under scalar multiplication, therefore the negative of this is y minus x belongs to y, and that is nothing but yx belongs to R. So now we have verified that this relation is reflexive, transitive, and symmetric. Right? The last one is symmetric property. So therefore R is an equivalence relation. And then whenever it is a equivalence relation, we use the notation x related to y if the condition is satisfied. So that means x minus y belongs to capital Y. And then we can define the set of equivalence classes. So here what will be the class of x? So class of x is x belongs to x such that x is related to y. So what will be this set? X belongs to x such that x minus y belongs to capital Y. Right. So what do we get here? So if so x such that, so I should use some different x than x1, right? So we are studying equivalent class of x, so that is this set. Now x1 and x2 are related, that means difference of x1 and x2, x1 and x is in y by the definition of equivalence relation. And then what does this means? This means x1 belongs to x, so that x1 minus x is equals to y for some element y in capital Y. Right. So now from this, if we write x1 in terms of x and y, then what do we get? We get here x1 is equals to x plus y. Right. So that means x plus y such that y is some element of capital Y. Right. So from this equation we have written x1 is equals to x plus y. So just we substituted x1 here, we get x plus y, and in this set we have all such element where y is a element of y. So now we have this set as a equivalence class, and such a set we usually denote as x plus capital Y. Right. So what is x plus capital Y? That is a set of all elements x plus small y, where small y is in element of capital Y. Right. So all equivalence class in this case are these sets. Right. So this is basically notation, and yeah. So therefore, what are the equivalence classes? The set of all equivalence classes in this example is the set x plus y for every x in x. Right. So in last example we have found what are the equivalence classes. Equivalence class of 1 and 2 odd and even number, because we know what is the equivalence relation, but here we don't know what is capital Y. Right. We started with capital Y, but we have not used it. We are abstractly defining, so that means set of all equivalence classes are of this form. So this we can find out if we know what is Y. Right, what is x and capital Y, then we can actually find this set. But here we are defining abstractly, and this set we will denote by x quotient Y. Right. So what we are saying is x quotient Y is the set of all equivalence classes coming from this equivalence relation, and this is known as quotient space. Right, the set of equivalence classes with respect to this relation is known as the quotient space. So why it is called space? Because it is a vector space, and we can define vector space operations. So basically addition, and scalar multiplication on x quotient Y. So for that we will take two elements to define vector additions. So first element is x1 plus y. We are adding into x2 plus y. Right. So they are of this form, and if we add them, the addition, how we will define? We first add x1 plus x2, and we'll consider equivalence class of x1 plus x2. Right. So this operation we are defining as a vector addition, and the scalar multiplication we are defining as similarly. So k multiplied to x1, the equivalence class of that. Right. What are these elements? Where x1 and x2 are elements of x, and k is a scalar. K is either real number or complex number. So you can easily check that this is a satisfies all the properties of vector space. So for example, what will be the inverse element? Additive inverse. So first of all, zero element. So if we have x1 plus y, then what element I add so that I get the same element? That is zero element, right? So what is the answer?
Any element of y.
Any element of y, but here we are considering such elements, quotient space.
Sorry, 0 plus y or simply y.
Yes, so 0 plus y, that is exactly the simply capital Y set, right? So what is capital Y? Capital Y is basically all the elements 0 plus y where y belongs to y. So that is exactly y only, right? So this is a zero element. So this is our zero element. And now if you know zero element, what is the inverse?
Minus x1.
Minus x1, right? So basically, therefore, minus x1 plus y is inverse, additive inverse of x1 plus y, right? So we have additive inverse and we have, so the other properties are easy verification. So mainly these addition properties are there. The other distributive and other properties you can verify later. Just check if you have any doubt. Okay, so any doubt in this example? If you have any doubt, you can ask. So this is one of the different example which you may not have seen in linear algebra. Example of quotient space. So whenever we have a vector space and its subspace, then we can define this quotient space. Okay, so let us see one example. So we know that if we take x equals to R2 and y is equals to the real line. So real line means the set of x comma 0 where x is a real number, right? So if we, yeah, so but before that, let us discuss the Cartesian product. So if x1, x2, xn are vector spaces which are finitely many vector spaces over field K, then we can define the Cartesian product x1 cross x2 cross xn which is defined to be the tuple x1, x2, xn. Each xi is element of capital Xi. Then this is a vector space and the operations are, so here we define coordinate wise operations. So if we x1, x2, xn, if we add with y1, y2, yn, so that is defined to be x1 plus y1, x2 plus y2, xn plus yn. So here it is not necessarily that x1 should be equals to x2. They may be different vector spaces and this operation may also be different. So we can also write as x1 plus y1, x2 plus 2y2 and plus n. So plus 1 is a operation on x1, plus 2 is operation on x2, plus n is a operation on xn. And similarly we can define scalar product. So that is also defined k dot 1 x1 to k nth scalar product xn. So where k is in k and x1 is in x1, xn in xn. And again y1 is in x1, yn is in xn. So we can define tens Cartesian product of n vector spaces. And example, we know that if we take the same vector addition and scalar multiplication of real and complex number, then Rn and Cn. So C is a set of complex numbers. Direct sum of R and direct sum of C are the examples of this. So the example which I was discussing is that if we take the vector space to be R2 with the coordinate wise vector addition and scalar product. We already defined vector addition and scalar product above. Right? And now we consider a subspace of these. So subspace is defined as x comma 0, where x is a real number. So this is basically x-axis, right? So is it clear that y is a subset of y is a subspace of x? x-axis is a subspace of R2. Is it correct?
Yes, sir. It will be a subspace.
Right, you must have seen that in linear algebra. So the two property of subspace we can check, zero element is there and difference is there. So why is a subspace? Now question is that what will be the equivalence class here? So what is the equivalence class of X? So that is X means here R2, so X1. So what is this? This is basically X plus Y, where Y is in capital Y. So what is X? X means element of R2. So let us write it as X1 comma X2 plus element of Y. So that we'll write as, let us say, X comma 0. So what had we said? X1, X2, X are real number. When we add this, what we get? We get X1 plus X comma X2, and X1, X2, X belongs to R. So what is this set? So if X is 0, then what we get? We get Y. Is it correct? If X is 0, what do we get? Yeah, so X is 0 means what? X is 0 means so I did some mistake. I'm writing here also X, I'm writing here also X. So let us correct that. Okay, so now X is 0 means X is what? X is X1 comma X2. That is 0 element. So if X is 0, we get X plus Y is Y, right? So what is that set? Whenever we take X1, X2 to be 0, we get X dash plus 0, where X dash belongs to R, right? So this is essentially our Y. So this we are verifying that 0 plus Y is Y, and when X is non-zero, so for example, if we take X to be 0 comma 1, so what we get here, if we take X equals to 0 comma 1, we get 0 comma 1 plus Y. So that set is X dash comma 1, where X dash belongs to R. So what is this set geometrically? All the elements X, X comma Y, X comma 1. So if we draw these points in R2, then what will be this set? All first coordinates, so that second coordinate is Y. क्या बनेगा ये सेट? So you take all the elements X dash, which is a real number. For example, X dash is 0, then we get 0 comma 1. That is here 0 comma 1. we take x dash is 1, then 1 comma 1, that is this point, right? If we take x dash is -1, we get this point, and in fact we are taking all points x dash, that means it is a line. So what is this line? This line is y is equals to 1, right? So this is a y is equals to 1 line. So the equivalence class of 0 comma 1 is y is equals to 1 line. Similarly, if we take equivalence class of 0 comma 2, then what we will get? This is a y is equals to 2 line, right? So what is happening is basically for every real number we are getting the corresponding line. So these sets are basically the distinct equivalence classes, and they are all the horizontal lines. So these horizontal lines will cover the entire R2 plane, right? So therefore here we are getting distinct equivalence classes. So what are the distinct equivalence classes? They are 0 comma alpha plus y, that is y is equals to alpha line, right? So equivalence classes are basically horizontal lines with different value of alpha, and this classes covers entire xy plane or R2, right? So equivalence classes forms a partition, we already mentioned earlier, and in this case the distinct equivalence classes, they forms the partition of the entire set X, which is R2. So this is a simple example related to geometry. Okay, any doubt in this example? Okay, then let us start a new topic, that is that also we know, that is a linear maps. So we have discussed some examples of vector spaces. Now we want to study certain linear maps. So we know that linear map P from a vector space X to Y is a map satisfying two conditions. So what is the condition? It preserves the addition and scalar multiplication. First condition is t of x1 plus t of x2. Right? It preserves the addition and it also preserves the scalar multiplication. All x1, x2 in X and k belongs to K is a scalar. So corresponding to given linear map, there are two associated subspecies. Right, so every linear map is associated to two subspecies. One is called the range and the other is called the kernel or null space. So the first one is defined as range of T. So range of T is basically all the elements of the codomain such that T of x is y. So is it clear this is a subspace? ये किसका सबस्पेस होगा, x का कि y का? Range is a subspace of x or y? T is a map from
Y.
x to y.
Sir, why?
Right, y, correct. Because basically we are taking all the elements of y. So range is a, or T is a subspace of y. Is it clear that it is a subspace, or do I need to discuss that?
No, sir, it's clear.
It's clear, right? You just take two elements in the range and verify that it is a close under addition and scalar multiplication. So this first example. Second is a kernel. So kernel of zero set of T or a kernel of T, or the third name is null space. Defined by, so zero set we defined as the set of all elements in X such that T of x is 0. Right. So clearly this is a kernel of T is a subspace of domain. This is also easy to verify. You take x1 and x2. If T of x1 is 0, T of x2 is 0, then T of x1 plus x2 is 0, provided T must be linear. If T is not linear, then this is not a subspace. Right. So we are using the properties of T is a linear map to verify that Zt is a subspace of X. So if kernel is a whole space, kernel is X, then we denote T to be zero map. Right. So if we have a linear map whose kernel is entire space, entire domain, then that means on every element of the domain the function is zero. So that means it is a zero function, identically zero function. And then we know certain results in terms of injectivity of linear map and kernel. So it is easy to verify. T is 1 function. So 1 means it is injective if and only if its kernel is 0. So sometimes kernel is written as n of t, right? But here we are going to use either, mostly we will use zt symbol. Right? So the function is 1, if and only if kernel is 0. So again here we are not mentioned, but we are taking T is a linear map. If we don't take T is a linear map, then this result is not true. Right, so linearity is useful several places. In this result also we are using T is a linear map. So whenever T is injective, we can define inverse map from the range of T to the domain. So we define T inverse on the elements of range, and we define it to be X whenever T of X is Y. So usually we cannot define T inverse, but we can define it whenever T is injective, because in general there may be two elements, T of X1 is also equals to Y and T of X2 is equals to Y, but X1 and X2 may be different. But now we are assuming T is 1 function, so that means X1 and X2 must be same, right? So that is what used here. So whenever there is a unique element except that T of X is Y, then we can define inverse on the range using this relation. So did you check that T inverse? What can we say about T inverse? Is it a linear function? We started with capital T, which is a linear and injective function, and we define T inverse on the range. So T inverse is a map from vector space to vector space, because the range of T is a subspace, so it is a vector space. Now question is that whether T inverse is linear map. So that is true, that note that T inverse is a linear map, and verification is very simple, right? Because if we take two elements, so let T inverse of y1 is x1 and T inverse of y2 is x2. Then what can we say about T inverse of y1 plus y2? So what is this? This is T inverse of y1. So if T inverse of y1 is x1, then we get T of x1 is y1. Right, so let us substitute here. So we get T of x1 plus, similarly, this gives T of x2 is y2. So this is T of x2, right? And then we know that T is linear. So this term we can write as T of x1 plus x2. And then T inverse and T will cancel out, right? Because T inverse on range is the same element. So that is x1 plus x2. And x1 plus x2, we know that that is T inverse y1 and T inverse y2. We proved that T inverse preserves the addition. Similarly, We can easily verify that. Here we use that T preserves addition. Similarly, we can use T preserves scalar multiplication, and we can show that T inverse of Ky1 is K of T inverse y1. So whenever T is injective and linear map, T inverse from range to the domain is defined, and as well as it is a linear function. Now some more definition. So the dimension of T is known as rank of T. T is a linear map. The dimension of range is known as rank of T, and if it is a if dimension, if rank is finite, so that means it is a finite rank operator. So such a map are called finite rank map. So at the end of the course, we will study compact operators. So they are compact linear maps, and there this concept is useful, that finite rank operators, its limit we get as a compact operator. So similarly, we can define the dimension of the null space, which is known as nullity. Right, nullity of T, and then we have the rank nullity theorem. What this says, rank of T plus nullity of T is equals to dimension of what, X or Y? So can you recall this result from linear algebra? Rank plus nullity is always dimension of the domain, right? What is T? T is a map from X to Y. It is a linear map. So then rank of T plus nullity of T is always a dimension of domain. Okay, so this result has a simple corollary, that whenever we have a null space 0, so that means range, dimension, and dimension of X is same. In that case, we get the map is onto. So T is a map from X to X is injective if and only if T is onto map. So there are certain examples of linear map which are very useful. So they are known as linear functionals. So a linear map linear function from a vector space to the one-dimensional space. K. So K is either R or C. So if it is R, its dimension over R is 1. Similarly, if K is C, then dimension of C over C is 1. In that case, it is a one-dimensional function. So a linear map, let us say it is F, linear map F from a vector space X to one-dimensional space K is called a linear functional on X. So what are the simple properties of this linear function? So suppose we take let F from X to K. You can take K is R or C, be a linear functional on X. So if F is a non-zero function, right? If F is a zero everywhere, then there is no point of studying it because that is a trivial function. So suppose F is a non-zero function. So that means there exists element x1 in X, so that at this point the function is non-zero, right? So at this point the function is non-zero, and we know that range is one dimensional, so that means rank can be at most 1, right? So rank can be at most 1. From that, what we can say, so if we take any element of X, then we can find unique element in the zero space of F, and we find an element K scalar such that X we can write as a x naught plus K times x1. So what will be K here? So let us find out K. So to find K, we apply F both sides. To apply the linear function both the sides, what we get, fx equals to fx naught plus f k x1. But f is linear, so that means we can write fx naught plus k times fx1. Right, the scalar will come outside, and moreover, what we know that x naught is element of kernel. So that means this value will be 0 plus k times fx1. So finally what we get is we get k is equals to fx divided by fx1. Right, so if we can write x in this form, then k must be this one. Right, so therefore what we get, so x equals to x naught plus kx1, where k is this element fx divided by fx1 x1. So now what is x naught? Because we know x1 is fixed. That means what is x naught? X naught is nothing but x minus fx divided by fx1 times x1. So if we have a linear functional f and it is non-zero at some fixed point x1, then every element of the domain we can write in this form, where k is fixed and x naught is fixed and x1 is anyway fixed because that is a fixed point, right? X naught we already fixed earlier. So x can be written uniquely as x naught plus kx1, where this element is in the kernel of f. So that gives us a unique decomposition of every element of the domain. So this decomposition is sometimes useful. What does this gives? This gives that the span of kernel of f union this element x1 is the entire space. So basically what we proved is this element covers all the elements of x. Alright, so what is use of this result? So use is that if we have G is another functional defined on x such that the zero space of G is same as zero space of f, and G of x1 is f of x1. What is x1? X1 is the fixed point where fx is non-zero. At this point, if G function also takes the same value and null space of f and G is same, then f is equals to G. So what is the proof of this? To prove this, we need to apply f on x, and we already observed that x is of this form. So that means x we can write as f of x naught plus kx1, and then f is linear, so that means we can rewrite this as f of x naught plus k f of x1. F of x1 is gx1, and x naught is a element of kernel. Right? This belongs to kernel of f, but kernel of f is kernel of G, so that means G of x naught is also 0. Right, so x naught is in kernel of f, that means is 0 plus k. F of x1 is G of x1, and G of x naught is also 0, so we can rewrite this in this form. And then again G is linear, so this is x naught plus kx1, so that is exactly G of x. This is true for all x in the domain. So that means the function is pointwise same, so that is same on the entire set. Okay, so I think this should be enough for today's lecture. If you have any doubts, you can ask now.